Okay, good morning. So we start a new chapter, chapter 5, which is about center of mass and linear momentum. So you see this picture, someone is throwing a bat, and you see that while it is moving, it's spinning, right, rotating as well. But one point in that bat is not rotating. Everything, all the other points are rotating, spinning around that point. That is the center of mass. So you can get that point, which is the center of mass point. We can apply the Newton's second law for this object, although it is doing all the spinning and at the same time moving. We can apply the Newton's second law for that center of mass point and treat it as obeying like a point particle. It will describe a parabola. So this is a free falling object in the sense there's only gravitational force acting on it. So if we can say the whole object is concentrated at the center of mass point, the center of mass point will describe a parabola. So this is the whole idea of the center of mass point. So we will see how we can calculate or find the center of mass point for extended object. Now we cannot consider objects to be any more like a point particle. So we move in and try to tackle the problem where an object has a size. The content of the chapter, section 1, will define the center of mass. Then in section 2, we'll define something called momentum. I don't know how many of you heard this word before in physics context, and impulse. Then in section 3, we'll apply the Newton's third law to internal forces, forces in a system, not external to the system. They will come in pairs, as you know, any force come in pairs. Then for this, what we define the momentum, we see there is a conservation law is applied to the momentum. Now you should know what conservation in general mean. Conservation mean something that does not change, right? Neither increase nor decrease, so that we say it's conserved. So we have what we call the conservation of linear momentum. This is a very useful principle. Using that, we can solve many complex problems. So let's start with defining the center of mass. So it is simply, if we have an extended object, we break that object into small masses, say M1, M2, and so on. And the center of mass of this object will be located, it doesn't have to be necessarily inside. Let's say this point is X center of mass and Y center of mass, where we can think of the whole weight of the object is concentrated at that point, which is called the center of mass. It is defined as the R center of mass, which gives both all X, Y, Z in one stroke, will be equal to the M1, the position of this, say this M1, say this position of this is R1. So M1 R1 as a vector plus M2 R2 plus we add all of them and so on, M3 R3, divide by the total mass, M, or in other words, sigma Mi. M1 R1 plus M1 R2, M2 R2 plus M3 R3, add them all and divide by the total mass. That will give you the center of mass position of this extended object. So the R center of mass will consist of the X center of mass, Y center of mass, and the Z center of mass in general for three-dimensional. So we can write this separately for each of them. So the x center of mass will be 1 over total mass into m1x1 plus m2x2 plus m3x3 and so on, as many masses we have. And y center of mass will be similarly in terms of the y1, y2, and so on, and the z center of mass. So let's take the easiest example. Okay, let's say we have got two disjointed, not connected, point masses, point particle of mass m1 and m2. And I want to know for this two particle system where the center of mass is. With respect to some coordinate system, let's say I have the 0 of this, this is the x-axis, x equal to 0 is here, and m1 is at a distance of x1, position of the m1 is x1, and position of m2 is x2. So our task is to find where is the center of mass of these two objects. Now, if I tell you, say m1 is equal to m2, we can kind of guess where the center of mass is. Right? Say this is 1 kilogram and this is 1 kilogram. The center of mass will be in the middle. Okay, so that is, but if the masses are different, they are not going to be in the middle. It will be closer to the heavier one or the lighter one. Heavier one. Okay, so that's you have a common sense feeling for the center of mass, right? Okay, so we have a formula to calculate the center of mass, which is, so now here we need to worry only about the x center of mass, because this is points, okay, located, both of them are located in the x-axis. So the y center of mass will be 0 anyway, because it is, both of them have y equal to 0 and y equal to 0. X equal to x1 and x equal to x2. Y center of mass, we don't have to worry about it. It will be, the center of mass will be along the x-axis. So that means y center of mass is 0, z center of mass is also 0. So x center of mass will be m1 x1 plus m2 x2 divided by m1 plus m2. Since we have only two objects, if there are three objects, then we will have to go m1 x1 plus m2 x2 plus m3 x3 divided by the total mass, which will be m1 plus m2 plus m3. Now, there are nice tricks with this center of mass. Also, we call it center of gravity. There is no difference between center of mass and center of gravity, because, if you take this equation, I can replace m1 by the weight, m1g, m2 by its weight, m2g. So this will be the, you multiply up and down by g. So the gravity, center of gravity will be, instead of the mass, we have the weight 1x1, weight 2x2 divided by the total weight. So center of mass, because the gravity g value doesn't change. It doesn't depend where it is. It's a constant. So center of gravity is equal to the center of mass. So there are some neat tricks with the center of gravity, center of mass. So please, I'm not going to open it now, but I recommend that you click on this link and look at it. It's fun. So let's do this example question for center of mass for water molecule. So water molecule consists of 3 atoms, right? 2 hydrogen, 1 oxygen. So we can ask this question, where is the center of mass of this water molecule? Okay, so it has got some symmetry. We look at the picture in the next slide, but let me read the question first. We know oxygen is 16 times as large as the mass of the oxygen, 16 times as large as the mass of the hydrogen. You know it from the atomic mass, right? Hydrogen atomic mass is 1, oxygen atomic mass is 16. Okay, right. So from that, you know their relative mass. So since in the center of mass equation, we have the mass coming up and down, all you need is the relative mass of the two. It doesn't matter which unit you put it in. We can put it in kilogram or gram or atomic mass, it doesn't matter. Okay. So he is asking, what is the distance between the center of the oxygen atom and the center of mass of the water molecule? And here he is giving some pico mean 10 to the minus 12. So because the distance are in picometers, pico mean 10 to the minus 12. So, but we need some data to answer this question. This is in the picture, we have got the data. So this is the oxygen molecule and this is the hydrogen molecule. So we know it is symmetric about the oxygen atom. There is no reason why it shouldn't be symmetric, right? Because hydrogen on both sides. And from the chemistry of the water molecule, we know that the angle we know, okay. So the angle between the two hydrogen atoms, this is the hydrogen bond here, 104.45. And we also know the bond length is 95.84 picometers. Now, this is the hydrogen molecule. This is the oxygen molecule. Where is the center of mass? From symmetry, we know it must be, if I call it y-axis, it must be in the y-axis, right? There is no reason why it shouldn't be in y-axis. It must be on the y-axis. So that means if I take the x-axis here, so oxygen is at the 0, 0 coordinate, okay? So from oxygen, where is the center of mass of this water molecule? It must be in the y-axis. That means x center of mass is 0, right? X center of mass is 0. It must be in this. Any point in the y-axis, what is the x value? 0. So x center of mass, we don't have to do it. We only have to find the y center of mass. So let me go to the next slide. So the calculation has been done. Okay. Now I'm going to take the, I'm going to tell the position of the left hydrogen atom to be x left, y left. We know them, okay, we can get it, but let me call it XL, YL is the position of the hydrogen on the left side. And the position of the hydrogen on the right-hand side, let us call it XR, YR, okay? And this angle is given, but anyway, I am going to call this as alpha, and this will also be alpha. We can get alpha and XL and YL. So XL is equal to this. Do you understand why it is so? This is 95.84 and this is alpha. So XL will be this. So from trigonometry, you know XL is equal to 95.84 multiplied by cosine alpha. That is the definition of cosine alpha, from the definition of the cosine alpha. So alpha, can you find alpha? 2 alpha plus 104.45 is equal to what? 180. So we can find alpha, right? Alpha can be found. So I'm not doing the calculation there, so you know how to get it. So we know alpha, so we get this answer. Why is it negative? You understand why it is negative. The left-hand side hydrogen atom is to the left of the 0, so it is negative. And why is, instead of cosine, we have the sine, it is also negative. So you know XL and YL. What about XR and YR? Similarly, only the difference is they are positive on the right-hand side. So we know XL, YL, XR, YR. So let me draw this table and get the position of the code oxygen atom. Oxygen atom is easy. It is 0, 0, right? Then hydrogen on the left, X position is this, Y position is this. Oops. Y position of the hydrogen is this. Then hydrogen on the right-hand side is the same thing with the positive. Okay, Y position is negative, right? Even for the hydrogen atom, Y position is negative, X position is positive. What is this? The masses. This is the X position, Y position of the oxygen, hydrogen left, hydrogen right. And this is the Y position. This is the mass will be. Do I have to put it in kilogram? No need. We will put it in atomic mass. So oxygen is 16, hydrogen is 1, and hydrogen right-hand side is also 1. We don't have to worry too much about the unit because what we are having is a ratio up and down. You know, there is no need to convert it into kilogram because it will be the same factor on the denominator as well as the numerator. So they are going to cancel. Right. So this is already we know X center of mass, Y center of mass. We use the equation. What is the equation? M1, that is M of oxygen, multiplied by X of oxygen, plus M of left hydrogen, multiplied by X position of left hydrogen, plus M of right hydrogen, multiplied by X, not X, Y. Okay, we're done with the X, so it is Y position of oxygen, Y position of left hydrogen, Y position of right hydrogen, divide by the total mass. So that is what is being done here. So 0 for the Y position of the oxygen, and this is the Y position of the left hydrogen. This is the Y position of right hydrogen, divide by the total mass. Total mass, masses are up and down in atomic mass unit. So we get the answer. Okay. Right. We are done. Yeah.
Explain for me sigma, please.
Sigma. Okay, sigma. Say for example, sigma xi means what? I is equal to 1 to n. It is equal to x1 plus x2 plus x3, however many n's we have. That is what the sigma symbol means. Okay, so we can write the equation for center of mass in terms of the sigma symbol. Let me explain this. So this means, let's say we have here three particles, right? So it will be sigma mixi mean m1 x1 plus m2 x2. So the I equal to from 1 to n. So how many n's we have? 3, right? So m1 x1 plus m2 x2 plus m3 x3 divide by m1 plus m2 plus m3. Here the sum of the product mx, here the only m. Good? Okay. So here we are showing how to get the center of mass, which is also the center of gravity, not from calculation, but experimentally. If it is a, symmetrical shape, like for example, a square, symmetrical, homogeneous, made of the same material, the center of mass or the center of gravity is very easy. It will be the geometric center. For a square or a rectangle, how do you get the geometric center? You draw the diagonal. Where the diagonal crosses is the geometric center. And for a symmetric, homogeneous object, homogeneous, it is important. Homogeneous means made of the same material. The density is the same. Center of mass is the same as the geometric center. But let's say we have an odd-shaped object. Is this a symmetric object? No, it is not symmetric, right? But however, we can determine this center of gravity or the center of mass kind of experimentally. How? We take this object, which is this odd shaped object, and tie it to one point, let's say A, point A. So we call this point B and point B. Tie a string to the point A and hang it. Then you can take a red color or something. You draw the vertical line on this object. You draw the vertical line, extending this. This is a vertical line. The string, it will be hanging. Okay, so it will be aligned like this. So continue this vertical line. Draw. Let me say I draw it in red. Fine. Then next, you untie this and connect it to the point B. Now, I already have this line on the object. It's in red. Okay. Now you hang it at point B. Now, again, draw the vertical line while it is hanging. Now let me put it in green. So where these two lines intersect is where the center of gravity is. So that is how you find the center of mass point experimentally. So you hang it first at one corner, draw the vertical line, then hang it from another point, then draw the vertical line. Where these two lines crosses is where the center of mass or the center of gravity is. So you can confirm it. Now let me hang it at the point C. It should go through the same point which is already drawn. So this is your first line. This is your second line. Now the third one, when you hang it on point C, it will exactly go through that point. So this is how to determine the center of gravity experimentally. Yeah. No. In fact, for two-dimensional object, two lines are enough. Okay, we can stop here. For three-dimensional object, you need to do it with three separate points. Okay. So it is difficult to draw three-dimensional object on a piece of paper, right, or on a screen. So some examples of the center of mass, the shrubs, trees that grows, individually. I mean, in an individual tree, not in a forest, they are both the same species. I think when they are grown separately, you tend to see the center of mass of the object is at the bottom, right? So more leaves at the bottom. But in a forest, what happens? There is a competition for the sunlight, right? They grow, so the leaves has to be at the top. So for this tree, the center of mass is at the top. Okay, because it is heavier, more mass is here. So center of mass will be towards where the more masses are. So we have got a question, concept question, to see, test you on the center of mass. This is a baseball bat. It has this odd shape, more mass on this side than on this side. You can move your finger to the right or the left until, like, you can take an odd shaped object and you can move it, and at the end, it will come and stop at the center of mass. So it is balanced, right? So this is where the center of mass is. So here we found the center of mass. Now the question is, what is the question? In the next slide, once the bat is balanced, which of the following statements must be true? The portion of the bat on the right-hand side is equal to the portion of the mass of the portion. Okay, the portion of the bat on the right side of your finger is equal in mass to the portion of the bat on the left of the finger. Let me go back. What he's saying is this mass, okay, let me call it ML, and this mass Let me call it MR. Are they equal?
Yes, because the thing is missing.
Yeah, true. This is where the center of mass, right? This is the center of mass. So let's say this x, this is 0, 0, okay, 0, okay, x equal to 0. Let me take the x. So x center of mass is 0, okay, because let me put the x equal to 0 there. So we know this is where the center of mass is. So x center of mass is equal to 0. Now my question is, you have to check the statement. The first statement says ml is equal to mr. Is it correct? No. The answer is no. Okay. Next statement. The portion of the bat on the right side of your finger is equal to in length to the portion of the bat on the left hand. Now, what he is saying now is the second statement. Let me call this is this length is dl, and this length is dr. dl is equal to dr. Is that correct? Also no. Okay. What is correct is ml x dl is equal to mr dr, because that follows from the definition of the center of mass. X center of mass is 0, right? So we know x center of mass is equal to mr dr plus ml dr divided by, well, one of them is negative, one of them is positive. So dl is negative plus m1 plus m2. So that means this is 0. So that means ml dl is equal to mr dr. So you cannot say ml is equal to mr. You cannot say dl is equal to dr. You can only say the product md is equal. Okay. So what is the correct answer? None of the above. Yeah. Yeah. Yes.
So it's balanced.
It's balanced.
How should we balance it if the masses are not equal on two sides?
Yes. Okay. So what happens? The weight on this side is at the center of mass of this portion, right? The weight of this one is the center of mass of this portion. And the weight on the other side is the center of mass of this portion. So what is going to be equal? The weight multiplied by this distance the weight multiplied by this distance, that's the position of the center of mass, is equal to weight multiplied by that distance. Well, the mass not equal. If it is a uniform object, okay, you will get the center of mass at the center. Then the masses are equal. If the object is not uniform, this is not a uniform. Okay, so then you will not balance at the geometric center. You will be balancing somewhere like here. Okay, let me make. Yeah. This is not the geometric center. This is the center of mass, because this is not a symmetric object. This is not a symmetric object. Okay. Let me draw it like this. Okay, let's say. So when you balance, it will be balancing somewhere close to this. It doesn't mean this mass is equal to that mass. It only means this mass multiplied by this length is equal to this mass multiplied by that length. It follows from the definition of the center of mass, but I can explain more, but I don't want to spend too much time on it in terms of the weight. Let me give an easy example. Maybe you will agree with me at least. Say, seesaw. Seesaw, right? So let's say you are sitting here and you have a weight of, let's say, 70 kilograms. And here, a child is sitting. Let's say she is only, say, 30 kilograms. Will you be balanced? No, you will not be balanced. So the center of mass of this is not at the center, it is somewhere here. Okay. Now, can you say this mass is equal to this mass? No, right? Okay. Right. So we will go to center of mass velocity. So we got the center of mass position. Now, center of mass position, if I write it for just the x center of mass, is equal to summation of mass position divided by the total mass. So if I divide both side by the time, so delta x over delta t, and this side is also time, but I'm not really proving anything, but we get the expression for the center of mass velocity from the center of mass position like this. So instead of here, we have the x center of mass, we have the v center of mass. So instead of the position, we have the velocity of each mass. So the velocity of the center of mass will be m1 v1 plus m2 v2 plus m3 v3, as many masses we have, divided by the total mass. So it follows from the definition of the position center of mass. So from position center of mass, we get the definition for velocity center of mass. So maybe we can have two particles with different position. Mass is m1, position is x1. Mass m2, position x2. And they have different velocity, v1, v2. So now I can define what is called the velocity of the center of mass of these two objects. Individually, they have different velocities, but I can talk about the velocity of the center of mass of these two systems. So they may be going in different direction. Let me give a very nice example to understand this concept. Let's say we have two masses, both are 1 kilogram and 1 kilogram. Where is the center of mass? At the center, right? Because they are two masses equal. So the center of mass will be at the center. Now, if they are at rest, what is the center of mass velocity? Velocity of the center of mass is also 0, also at rest. Now, let's say this is going to the left with the velocity of 1 meter per second, and this is going to the right at the velocity of 1 meter per second. What do you think will happen to the center of mass point? Will it change? No. So the center of mass velocity is 0. Although individual particle having different velocity, but the center of mass point is not moving. Okay. So the center of mass velocity is 0. This equation, give it correctly, because here it will be m1 x v1 plus m2 v2. v1 is plus 1, v2 is minus 1. So m1 plus v1 plus m2 v2 will be 0. So that will give you the velocity of the center of mass is equal to 0. Okay, good. Now, this quantity, this mv, is called the momentum of an object. Okay, that's it. So if someone asks you what is momentum, we have a very simple, straightforward answer. There is nothing mysterious about it. If you ask what is the momentum of an object having a mass and velocity v, what's your answer? Mass multiplied by velocity. That is the momentum. That is the momentum of an object. The momentum of the object is the product of mass with the velocity. So since velocity is a vector, momentum is also a vector. What is the direction of that vector? Same direction as the velocity. Mass will have no effect on the direction because mass is not a vector, right? It has no direction. So the direction of the momentum is the same as the direction of the velocity. Excuse me, please stop talking. So what is the summation of all the momentum? meaning the total momentum. So you can say the velocity of the center of mass is equal to total momentum of the system divided by the mass. Okay, velocity of the center of mass is equal to total momentum of the system divided by the total mass. So other word, you can say P total is equal to total mass multiplied by velocity of the center of mass. So we, if individual particles have different momentum, and the total momentum will be simply mass, the total mass multiplied by velocity of the center of mass. Linear momentum and impulse. Now momentum, and we get this adjective linear because later on we don't cover it, but there is something called angular momentum also. That's why we call it linear momentum here. But anyway, you only have to know about the linear momentum. So I will just say momentum, it is understood. I'm talking about linear momentum. We are going to introduce another concept called impulse now. Okay, so we did center of mass, it's a new concept. Momentum, another new concept. Then we are going to introduce another one, impulse. So what is impulse? To get to that, we'll go there slowly, right? So this is we'll start with the definition of momentum. Momentum is equal to mass into velocity. If I take the derivative, meaning divide by time, derivative with respect to time on both sides of the equation, then we get this one, change in the momentum divided by the time. That's how fast the momentum is changing. Now, if this side we have change in the velocity, rate of change of velocity, what is it? Acceleration. So that's the definition of acceleration, rate of change of velocity. So for this, I can write A, acceleration. So now recognize this. This is what comes in the Newton's second law. Mass into acceleration is equal to net force, right? So instead of mass into acceleration, I can write the net force. So now we have the Newton's second law can be expressed as in a different way. You can also say that net force is equal to rate of change of momentum. This is an alternate expression for the Newton's second law. In fact, when Newton introduced his second law, he gave it like this, not as mass into acceleration. He said the net force is equal to rate of change of linear momentum. So I can rearrange, I can bring this delta t to this side, and I got this. So this tells you the net force multiplied by the duration of the action of the force. Suppose the force is acting for a short time. Let's say there is a force or net force acting on an object for a short period of time, delta t. So the product of the force with the duration of the force is equal to the change in the momentum. It's like hitting a ball with a bat, okay? Hitting a tennis ball with a racket. So is the force is acting for a long period of time? No, for a short period of time. So the force acting on the ball multiplied by the duration within which it is acting on the ball is called the impulse. This F into delta t is called the impulse. So this has a name. The symbol we use is J. Some people use I, some books use I, but we will choose J, okay, not I. J is called the impulse. There is a force acting on an object, force or forces, okay, a net force acting on an object for a period of delta t. It will change the momentum in that the impulse is equal to change in the momentum. This follows from the Newton's second law again. So the impulse of a force is equal to change in its momentum. This is also called the impulse momentum theory. Okay, impulse momentum theory. So it's also the definition of impulse. Definition of impulse is this, okay? The definition of impulse, we are going to call this as the impulse. So that's the definition of impulse. So I can say J is equal to change in the momentum. This follows from the Newton's second law. This is the impulse momentum theory. J is equal to delta P is the impulse momentum theory. The definition of impulse is F into delta T. Okay, so we can get the impulse. If you know the force, multiply by delta T, you will get the impulse. But the problem is, this is okay if the force is a constant force. But when you hit a ball with a racket, do you think during the period within which it is acting, it's a constant force? No. It is like this. When it touch the ball, it will have a zero force, and the force will become great, come to a very big value, maybe thousands or 10,000 Newton. Then as the ball leaves the racket, this whole thing will happen in a time of a fraction of a second, millisecond or even microsecond, depends. But it is not a constant force. It's not like this. It is not a constant force, but it is a varying force, come to a high value, then dying down. So that's what usually happens. So, but however, to get around this problem, because we know it's not a constant force, we kind of say, okay, in this, the impulse is actually the area under the curve for a varying force. For a varying force, it is the area under the curve. If it is a constant force, it is, you can see, it is the area, right? Because it is F multiplied by delta T. What is F multiplied by delta T? It is the area if it is a constant force. It is not. It is a varying force. So we define an average force such that the area that comes under that average force is equal to the actual area of the actual force. So that's how we define the average force. Let me take the attendance and I will continue. So I hope you understood that. Okay, the definition of the impulse is F into delta T. But F, if it is a constant force, no problem. We can get it by multiplying the. If it is not constant, which value did you put? We have to put some average value, right? How do I get the average value? So that's how I explain with the graph here. Suppose it varies like that, then the impulse will be the area under the curve. Okay, so how do I know it is area under the, suppose it is a constant force, you can see F into delta T is the area under the curve. So even for a varying force, it has to be the area under the curve. So we get the average value for this force by drawing the average such that it will give you the same area as the area for the actual force. That's how you get the average force. Right. Now we come to the next section actually. Yeah. Don't worry. Okay. So, I mean, you get the idea, right? The concept, you got it. How actually get a number for it? I mean, we use this. I mean, what happens is we use this theorem. Sometimes we know the change in the momentum. So we suppose the final momentum and the initial momentum we know for a certain problem. We can find change the momentum and we say it is equal to the impulse. And impulse is equal to average force multiplied by delta T. And if I know the duration within which the ball is in contact, how much time it has, the force is applied on the object, then we also know this. So we know delta P, we know delta T. I can find the average force in an indirect way. Okay, that is one way of finding the average force. Or sometimes the average force will be given to you. and you'll be asked to find the other things. So here, I want to evaluate the net force acting on an object. So I can group the net force as the external forces external to the system. We are talking about system now, right? Maybe there are two objects, not just one object system. And for this system, there will be forces coming from outside, which we call the external force. And there will be internal forces, meaning forces that are due to interaction between these two objects or more than two objects. So those are internal forces. And you know, internal forces come in pairs. External forces also come in pairs, but the other object is outside of the system. But when you take the internal forces, the two forces are inside the system. So when you sum all the internal forces, it is going to be 0. Okay. Sum of all the internal forces for a system is going to be 0, because for every force, there is an opposite force equal in magnitude. So when you add them, it will be 0. So all the sum of all the internal forces will be 0. So the net force, if you want to get the net force for a system, all you have to do, ignore all the internal forces. We only worry about the external forces, because the sum of the internal forces is going to be 0. So we got this equation for a system, the Newton's second law. Net force will be only the sum of all the external forces equal to mass multiplied by acceleration of the center of mass. Not of each individual acceleration, we just go to the acceleration of the center of mass. So we got this equation, which is delta P over delta T is equal to net external force, change the momentum. What happens if the external force is also 0? Suppose, I'm not saying it is 0, suppose if the net force, external force acting on a system is 0, then when, okay, it's a when or if, then we have the rate of change of the total momentum is equal to 0. This is called the, if it is 0, mean what? The total momentum is a constant. It doesn't change with time. So the total momentum of a system remain constant if there are no external forces acting on the system, with the condition, it is not always true. If you have a system which is isolated, isolated means there are no external forces acting on it, then the total momentum of the system remain constant. This is the law of conservation of momentum, linear momentum. It's conditional. The condition is it is an isolated system, meaning no external force, or the net external force is 0. Okay. I will just start this question, then I will stop. An ice skater standing on ice is tossing a water bottle in vertical direction. Consider the skater and the bottle as a system. So we just first define our system. The skater and the bottle as a system. Is the momentum of the system conserved? Ignore friction. The answers are, there's a picture, I hope there's a picture. No. So there's a picture for this question. Okay. Anyway, let me draw the picture. So this is the skater and this is the bottle. She's throwing this bottle. Oh no, is it? Tossing in a vertical direction. Not throwing, tossing. Throw it up. Is the momentum of the system conserved? So this is the question now. She has the bottle on her hand and she's tossing it up. Now, standing, okay, she's not moving, she's tossing it up. Our system is the bottle and the skater. what is the condition for the momentum to be conserved? No net external force. No means zero net external force. There can be external force, but it is zero. What are the external forces acting on this system? The weight of the gravity, weight of the person, skater, weight of the bottle. Okay, that's it, right? Weight of the bottle, weight of the person. Now she is tossing it up, so vertically. Okay, so now ignore friction. So can you say the net force acting on this system is zero or not zero? If it is zero, the momentum is conserved. If it is not zero, the momentum is not conserved. Okay, the weight is balanced by the normal force, that is also external force. Okay, it's not an internal force. Weight is from the earth. Earth is not part of the system. And the normal force is from the flow. Flow is not also part of the system. So that is cancelled. What about the normal force between the bottle and the hand? These are internal forces, right? That is also. So the total momentum is conserved, right? Because the momentum of any system is always conserved, that is the wrong answer, right? You cannot say always any system is conserved. Yes, because the net external force is equal to zero, that is correct. Because yes is the correct answer. Okay, there is a variation of this problem, so I will not go to that. There is some more question. I'm sorry. Okay, the answer is no, not yes. Okay, I'm sorry. The moment, yeah. The answer is no, okay, not yes. So when you throw, when the bottle leaves the hand, the bottle's non-zero net force acting. As the skater tosses the bottle, she presses the ice with the force greater than the total weight of herself. So when what happened when you throw this, you need to apply a force on the floor greater than the total weight of herself and the bottle, which results in a greater normal force from the ice. So as she tries to throw it, what happens, it will be very small difference, but still, because the bottle has a very small weight, the moment she tosses it up, that will make the normal force from the floor on her slightly greater than the weight of her on the earth. So the answer is no answer. Okay. Right. So let's continue. I will take up this question again in the next class, then I will explain it again. Okay. Thank you.